Good evening, ladies and gentlemen. We're going to be going over the photoelectric effect this evening. All right, so we started doing the photoelectric effect in the lesson on Tuesday, and I thought I'd continue with that section today. I've actually done a little bit of a setup here where I can look at questions and have some space to solve them at the same time. But I thought what I'd start with, and it's what I've got down the right-hand side over here, is just a quick little bit of revision. I know I did touch on this during Doppler, but the idea of emission and absorption spectra. So with the photoelectric effect, we quite often look at what happens when light shines on a metal and an electron gets emitted. What we don't look at is, or what we don't always focus on quite as much, and we probably should, is what happens when that energy maybe doesn't cause the emission, and also what happens and is responsible for different colors of a whole bunch of things around us. And that is your electron transitions or energy transitions of electrons. All right, I'm only going to be working on the right-hand side. Please, I apologize. I do want to keep the layout for later. So the idea is that within an atom, if you've got your nucleus at the center, you guys all remember your board diagrams from years and years ago, all of your shells, and then you put your electrons in your shells. So for example, if I were to put certain electrons into shells, maybe this particular element has 4 electrons, okay? Those electrons would have specific shells that they fill. And we're used to the idea from early grades about these being energy levels. Now, it is possible for an electron to move from a lower energy to a higher energy. And that is what I'm going to be talking about now when I talk about transitions. It's electrons moving from one energy level to another. Now, to make life very easy, when we deal with this idea, we don't deal with atoms that have multiple electrons doing multiple transitions. We usually simplify everything and we only look at hydrogen, because hydrogen has just one electron. And that electron can do transitions to different energy levels. So it could go to here or maybe to here. When an electron goes from a lower energy to a higher energy, it must absorb energy, okay? And quite often, instead of drawing it in a round board diagram like that, we instead, let's try and do that a little bit more neatly, look at our energy levels just as simple horizontal lines, okay? And we call these the different energy levels. Please note the lowest energy state we can have is called E0. I usually call that ground state, but ground state's just technically the lowest. There's E1 and there's E2. Each of these energy levels would actually correspond to a specific value, usually a value of joules in the region of something times 10 to the negative 19. So there's a specific value associated with them. And when an electron jumps from one energy level to another energy level, it can only do this transition by absorbing energy, and it absorbs the energy of a photon. So if this energy happens to correspond, I don't know, I'm going to make up a number of, I don't know, maybe 3 times 10 to the minus 19 joules. If it has that amount of energy, then we can even use the formula E is equal to HF to work out exactly what frequency of light will be the photon energy that it will absorb to go from a lower energy to a higher energy. So that is an absorption, okay? Later on, if this electron has been absorbed and goes, if the photon has been absorbed to give the energy to the electron to cause it to go to a higher energy state, that electron could then relax down to the original ground state, and in the process, it will emit the energy, and the energy it emits will be equal to a certain frequency of light, and it will then give off a photon of light of that same amount of energy. So you've got to absorb a photon of energy or photon's worth of energy to go to a higher energy state, and emit or give it off to relax back down. Okay, so that's the first idea. Now what we need to do is to link this to what we see in emission and absorption spectra. So I'm going to start with what we call the continuous spectrum. Now, the continuous spectrum consists of every single visible color. And if we take white light, which consists of every visible color, please note, white light will be produced by the glowing bulb. And if we take this white light and we shine it through a prism or through a diffraction grating and prisms serve the same role, what it can do is it can cause the light to bend by different amounts depending on the wavelength of the light. Since V is equal to F lambda, if you have a different wavelength, you have a different frequency as well. So all the different colors of light get spread out into the spectrum. This is what happens when we make a rainbow. Okay, so white light, visible white light from the sun, from a candle, well, candles usually are not entirely white, or from a white bulb will produce all of the colors and you get a full continuous spectrum. If you've got a continuous spectrum, you should have every single frequency available. And therefore, since E is equal to HF, if every single frequency is available, so is energy of a full range across the spectrum. Now, we have two different kinds of spectrums that we need to know about, an emission spectrum and an absorption spectrum. And you need to know how to create these. Basically, if you know these two sets of diagrams I've got here, it's usually enough, but it's just to give you an idea as to how it all fits together. This question doesn't get asked very frequently, which means that when they do ask it, it's often quite a lot of guessing for some of you, where you're like, it's one or the other. We know it's one or the other, which one? So you need to make sure you have an idea. So we're going to look first of all at an absorption spectrum. An absorption spectrum is created when energy in the form of photons are absorbed. So if I have a white light source and I pass it through a cold gas, the electrons are going to absorb energy to go from a low to a higher energy. When they absorb specific energies, now the energies correspond to the difference from here to here, from one energy level to one other energy level. They can't make any energy transitions they want. They've got to go from one specific point where electrons can be to another specific point. A little bit like rungs on a ladder. You can't step on rung 1.5. You either step on rung 1 or rung 2. Non-negotiable. If you put your foot in between the two, you'll fall back down to the lowest one. And what happens here is the energy is absorbed, and that energy corresponds to the frequency of that color light, that color light, that color light, and that color light. What that basically means is when we've removed those lights, that specific frequency corresponding to a specific color from the spectrum, which was continuous, those now disappear. And this particular pattern is actually like a fingerprint for every different element. Different elements have different electrons, which have different energy levels and therefore can only make certain transitions. So therefore, when we look at an emission or absorption spectrum, it allows us to know which elements we're looking at. These are almost like fingerprints for different elements. This is one of the reasons why we know what elements we find in the sun. Nobody's been to the sun to go and take a sample and see which gases are there. We know that it's mainly hydrogen and helium because of the fact that the light that reaches us has all of the colors except for those that would be missing if hydrogen and helium had absorbed those specific colors. So we can see the emission and absorption spectrum and use them to predict what element is somewhere. You also, instead of doing the gaining energy going up, can do the releasing energy going down, and that would produce an emission spectrum. Now you'll notice that an emission spectrum is not the entire full colors. It effectively is only the colors that were originally absorbed are now being emitted. So there's one, there's one, there's one, and there's one. I took screenshots of these and they're on slightly different scales, but they should in fact be the exact same size and the exact same combination of lines. So if this gas now has got its electrons and they're excited to higher energy levels, it's hot, then they will slowly but surely relax down to a lower energy. When they do, photons will be given off. Not every single frequency of photons, only the ones that correspond to the exact energy changes that are made, and hence they'll be very specific colors. All right, so we start with the hot gas. It goes through a diffraction grating. All that the diffraction grating does is spread out all the different frequencies so you can see them in their individual places. And from that, we get our emission spectrum. So it's up to you at this point, I think, to go and actually memorize, and I do mean memorize that which spectrum is emission, which spectrum is absorption, and what they look like. All right. I hope that this makes good sense. When we talk about blue shifting or red shifting, as in the Doppler effect, what's effectively happening is all of these lines, instead of being in these positions, either shift and go, keeping the same distance, go slightly towards the red or slightly towards the blue. Okay, so that's just a little bit of an explanation to cover all of that, just in case it gets asked. All right, what I'd hoped to continue with you tonight, with you then tonight with, is this particular section here, which is us looking at some older past papers. I've specifically and very deliberately gone back quite a far way for us to go and look at specific questions that were done a little while ago. Okay, so you may not yet have done them if your teacher starts with the most recent papers. All right, so the first question says, graph P below shows how the maximum kinetic energy of the electrons emitted from the cathode of a photoelectric cell varies with the frequency of the incident radiation. So at the end of your lesson on Tuesday, we looked specifically at graphs, and we even looked at how we rearrange the equation and what the y-intercept versus x-intercept mean in a particular graph like this, as well as what the gradient does. Now, I'm going to assume that maybe some of you didn't attend that lesson. Maybe some of you have forgotten. And I'm actually going to go back and I'm going to do this particular graph from scratch. I do know that some of the students that I teach actually go to the point of memorizing. So they ahead of time will be looking at this going, but ma'am, we know exactly what the gradient is. And that's wonderful, but most people don't. So I'm going to start by saying that the energy of a photon is equal to the work function plus the EK max. Okay, apologies, we seem to have a helicopter overhead. I don't know if you can all hear it. From there, we can see that we're going to be plotting the kinetic energy. That value over there is my Y value. And then my X is the frequency, which means that I actually need to split E, the energy of the photon, up into HF is equal to W naught plus EK max. All right, so if we now look at this, that value is my X, this value is my Y. When we do straight lines, we always like to have Y is equal to MX plus C. I'm not going to give the full game away here. I just want to show you what we're doing. So therefore, I can have EK, that's Y, is equal to HF minus W naught. Okay, so at this point, I'm going to remind you that this becomes my Y, this becomes my X, and you need to therefore consider what is your gradient and what is your Y-intercept. I'm going to leave it at that point. So, because we're doing this not yet as a masterclass, but as an individual lesson or a normal lesson, I'm going to give you a chance to answer some of the questions, but some of them I'm actually going to work through with you and not give you tons of time where you have to think through them. So we'll do a little bit of practicing and getting used to the ideas before I give you tons of time to do them on your own. All right. So question 1.1 asks you to define the term work function. Can I ask anyone, does anyone know what the term or the definition of work function? Any volunteers? Anybody? I think it takes quite a long while to type up and not everybody's willing to put it in and type it all up. All right, yay, we do have a taker. So I've got here from a couple of people. The minimum energy required to emit one electron from a metal, that's an option. How much energy is required to allow an electron to be emitted? That's perfect. We've got a few more. Gosh, all right, just give me a second. I think all of you are busy typing at the same time. The minimum energy required to emit an electron from a specific metal. So I would say that the key idea here is that it is the minimum energy to emit an electron. And then I like you to put in the words here from the surface of a metal. But technically, I don't think they always worry about that bit for the mark. All right, but I guess the question is emit an electron from what? And it's specifically from the surface of a metal. All right, continuing onwards, you are then told to calculate the work function of the metal used as the cathode in the photo cell. And then lastly, secondly, when it will come to the end bit here, the velocity of the photoelectrons emitted when the frequency of the incident light is 8 × 10⁻14 Hertz. Now, ladies and gentlemen, I'm going to just quickly ask at this point, and I can see you, I know you can't all see, well, you're all busy looking at things online, but I can now see you. What I wanted to ask is, looking at that question, who feels that they're already able to answer it? Who feels that based on what we did in the last lesson and what you've been doing at school, you would be able to calculate both of those things? Give me a thumbs up if that applies to you. Okay. All right. Okay. Okay, so it's less than half of you. So I think, to be fair, I'm going to do the first bit with you. Please, if you feel you can do it completely on your own, by all means, mute me for just a second, okay? And then come back and have a look, or work it out without looking up, either of the above, and then we'll compare them in just a second. All right. I'm going to be working through this with the people that I don't think can yet do it, or are a little bit uncertain. Okay, so you do have your options for the first time we do this. So the first question asked us to calculate the work function. Now the work function is W0. If I look at this equation, W0 is going to be my y-intercept, which is a little bit of a pain because I can't actually see it, which is why they told you to calculate, not just to determine. So in order to calculate this, I've got to do a little bit more work. At this point, I also don't know the kinetic energy necessarily. So I may have to do a little bit of thinking around this. So what I would probably do here is I could either deliberately try to plug values into the equation and calculate the y-intercept. So that is one option. I can work out the gradient of the graph and then go from there. But let's be honest, I know what the gradient of the graph is. The gradient of the graph is Planck's constant. So I could, in fact, here, knowing this already, say y is equal to 6,63 times 10 to the negative 34 times by my x value. You didn't have to call either of these y or x, okay? You could already have gone in here with this being kinetic energy and this being frequency. I don't mind which you use, minus W0, which is what I'm looking for. So I would be able to substitute everything in if I knew a y and an x value, which I do, the coordinate on a graph. Now my advice here is to pick a perfect coordinate. Pick one where you're 100% certain of what it is. And this value right in the middle here for me is a very good example. The line cuts through perfectly. So I've got the frequency, and if I go across here, I've got the kinetic energy. Now you've got to be careful. The kinetic energy has 10 little blocks. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 between 4 and 8. That means that each little block is 0,4. So this is 4, this is 4.4, this is 4.8, this is 5.2. So my kinetic energy is going to be 5,2 times 10 to the minus 19. don't forget those units, is equal to 6,63 times 10 to the negative 34 times by my x. My x is 10 times 10 to the 14. Do not forget your scientific notation, minus W naught. I've chosen 1 point. You could pick any other point on the graph. There's another one there that's rather neat. There's one down the bottom that's rather neat. But make sure that you choose one that looks like it really goes through the corner of 2 points that you got an exact value. So 5.2 times 10 to the minus 19 minus, use brackets, 6.63 times 10 to the negative 34 times by 10 times 10 to the 14. There's the positive 14, good. If I do that, I get negative 1,43 times 10 to the minus 19 is negative W naught. So therefore the work function W naught is 1,43 times 10 to the minus 19 joules. Okay, now your answer may be slightly different to mine if you chose another point. Your point and your read-off may not be exactly the same as mine. So therefore, because of that, we would have to accept a little bit of a range of answers. What we would not accept is students who'd left off the times 10 to the negative 19 and the 10 to the 14, because then your answer wouldn't just be in the wrong range, it would be completely in a different range. All right, can I quickly ask, who would have managed to do that completely on their own? Let me just quickly find the right way to check. There we go, there all of you. Okay, so some of you would have been able to do that on your own. Okay, well done if that applied to you. Those of you who didn't yet know how to do this on your own, now you know. All right, so that was the first question. So that was 11.1. Then we move on to question 11.2, which asks you to calculate the velocity of the photoelectrons emitted when the frequency of the incident light is 8 times 10 to the negative 14. Sorry, 8 times 10 to the 14. Now you have two choices here. You could, if you wish, since you've gone and worked out the work function, you could take this value, plug everything back into the equation and solve. But you could also just use your graph. And according to your graph, that is 8 times 10 to the 14. And if you go up to here, okay, you end up with a mean point because it's halfway between the two. But I'm quite comfortable for you to read up, read across. That point for me is 1.5 blocks below. So I would say 1.5 blocks is 0.6 below. So I would take that value to be 3.6 times 10 to the minus 19. So you have a choice that you could either plug everything back into that equation, or since you've been given a graph, you can work from it. And you can say, well, the kinetic energy is a half mv squared. The kinetic energy, according to what I see here, is 3,6 times 10 to the minus 19 joules is equal to a half. The mass is the mass of an electron. You need to go and look for this. It is on your formula sheet. It's 9,11 times 10 to the negative 31 kilograms, and then multiplied by v squared. So if I take my 3.6 times 10 to the minus 19, I times it by 2 to get rid of the half. I divide it by, use brackets, 9.11 times 10 to the negative 31. I get that v squared is 7,90 times 10 to the 11, but I don't want v squared, I just want v. And I get that the velocity is 889,010,85 meters per second. Please note this velocity is only true from the cathode to the anode, not once it moves through the rest of the connecting wires. All right, ladies and gentlemen, can I just quickly double check with everybody that what I've done so far makes good sense to everybody. So I'm just quickly going to stop sharing. I know it's going to get rid of all of my writing, so please make sure that if you need to take a screenshot of everything or you need to take a picture, you do so right now. We'll carry on with the rest of this just now, but I think the rest of this is in calculations, so we can lose our information for now. All right, can I quickly double check? Does that make good sense to everybody, what we've just gone through? Okay, please, if it doesn't make sense, you need to try and identify what it is that isn't making sense, and then let me know so that I can assist you. All right, okay, let me continue again with the rest of the questions. All right. So we then move on to 11.3. The photocell is now replaced with another one where the work function of the cathode is twice that of the metal in the first cell. Now, I'm going to presume we don't need the exact value, but if we use the equation E is equal to W naught plus EK max, it effectively means that this is going to be twice as big as it was. Okay, so the maximum kinetic energy versus frequency graph, Q, for this cathode is now drawn on the same set of axes as P. So we're going to pretend that we draw this graph onto here. Now, what's going to happen, and what you may not have really realized, is that this over here is my threshold frequency, okay? Effectively, my work function, badly drawn down to there, is the negative y-intercept, okay? So this new graph is going to be drawn onto the same set of axes. So they're now saying that this is graph P, and we're going to draw on graph Q. Now, I'm going to suggest right now that we actually try and draw it on. So the first thing that you should note is if your threshold, if your work function is twice as big, Planck's constant stays the same, and your F naught will also be twice as big. So instead of being 5 times 10 to the 14, it's going to become 10 times 10 to the 14. The second thing that's going to happen, if you remember what we just proved over here, is, hopefully I'm going to quickly just jump to it, but we got that, oh no, we didn't get that, but we got that EK, I'm just trying to remember this, Y is equal to, I think we got H F minus W naught. That's what we got. We said that this was your Y, this was your X. That made Planck's constant your gradient and W naught your y-intercept. So what's going to effectively happen to our gradient is absolutely nothing. Planck's constant is fixed. So what we'll do to produce this graph is it's going to have exactly the same gradient, but it's going to have a y value that goes further back. And if we were to extend it all the way down to the end, it would end up having a y-intercept that was twice as low. So effectively, this y-intercept would then become negative 2 W naught. Okay, so I find that if I think through all of that before I even start answering a question, then the questions aren't going to get me caught off guard because I have a picture about what I'm looking at. All right, so us changing the work function is going to shift the entire graph down in such a way that it is parallel. So the question now says, how will the gradient Q, the gradient of graph Q compared to that of graph P? Write down greater than, smaller than, or equal to. Your answer is that it is equal to, because the gradient is Planck's constant. And you can mention that therefore it does not change. The next question asks us, what will the value of the x-intercept of graph Q be? Explain how you arrived at the answer. And I'd say something like that is probably how you arrived at the answer. but you can go and say here that since the gradient or the x-intercept is f0, f0 is twice, please you'd write that out in full in an exam, as large if W0 is twice as large. Something along those lines. All right, ladies and gentlemen, I don't think this was a particularly difficult question if you knew your theory. If you didn't know your theory, then this is gibberish and it makes no sense. All right, so I'm going to just quickly stop sharing and check, is everybody still with me? Does this still make sense? Good, okay. And then just before I race on, I'm going to wait for all thumbs to go down so that I can ask the next question. Okay, the next question I have to quickly ask all of you here is, who's already learned something new? Okay, fantastic. That's what we aim, well, what I'm aiming to do is that if you pick up even 2 new things in each lesson, that's 2 things you couldn't do before. There was a benefit. Okay, sometimes the knowledge that you pick up is just that you really do know what you're doing, and that's also fantastic. Okay, all right, so that was our first question to do. Let's move on to the second question. Since I've already done one with you, I may give you a chance to try this a little bit more independently this time, so you can do a little bit more of the calculations yourself. All right. Okay, just give me 1 second. Can I please ask a minion for a glass of water? Thank you. All right. The big minion. Okay. Question 10 says ultraviolet light is incident. Incident means shining onto a photocell. There's a picture of our photocell with a potassium cathode. There's the potassium cathode as shown below. The threshold frequency of potassium, please note this threshold frequency is actually a specific constant for each metal. It's one of those things that you can look up in data booklets. It is reported, it doesn't really change. So it's element specific. If you make an alloy, obviously, then it won't behave quite the same way. But if we're dealing with a pure element, it will. All right, so this threshold frequency means that our F0 is 5,548 times 10 to the 14 hertz. Okay, this is our photocell. There's our potassium or metal cathode. Light shines on it, that's a photon of light. There's our emitted electron, which we call a photoelectron, and there's our DC power source. All right, so the questions start. 10.1 asks you to define the term threshold frequency. All right, is anyone brave who can tell me what the threshold frequency is? Anyone? Okay, I'll give you a little bit of a hint, and I'm sure you're all busy typing, so I'm going to wait for you. But I find that I often get confused when I'm writing things down because I go into autopilot, and you can easily get confused between the work function and the threshold frequency because the difference between the two is very subtle. So Michaela's already given me the right answer. It is the minimum frequency required to emit an electron from a metal surface. If you look at that, that's exactly the same as your work function, but instead of saying the minimum energy required, you say the minimum frequency to emit an electron from a metal surface, from the surface of a metal. So this is the minimum frequency of light required to emit an electron from a metal surface or from the surface of a metal. All right, the maximum speed of an ejected photoelectron is 5.33 times 10 to the 5. That is your V. the velocity of the emitted electron. All right, so what I'm going to give everybody a chance to do is to calculate the wavelength of the ultraviolet light used. In order to be fair, I'm going to give you all of the formulas that you would have on your formula sheet. So I'm going to tell you E is equal to W naught plus EK maximum. I'm going to remind you that E is equal to HF and that E is equal to HC over lambda. All right, ladies and gentlemen, I'm going to work this out as well. I'm going to share my answer with you in just a second, but I actually want to give you a chance now to do some of this on your own and see how much of it you get. All right, please go for that right now. Just in case anyone doesn't know their constants, I'm not writing it down because I don't want to have to share my screen with you. But Planck's constant is 6.63 times 10 to the negative 34, and C is 3 times 10 to the 8. Both of those are on your formula sheet, but you do need to start practicing and learning where to find them. I'll check in just a second. I know that there's a question. Unit for what? Okay, so just quickly, the unit of wavelength is meters. It's a distance. Okay. All right, who's got an answer? If you do, can I ask you to just quickly type it in so that I can check? Okay, Sarah, I agree with your answer, but I don't like your scientific notation. I've got a very different, there we go. Thank you. I was going to say you're missing a couple of like gazillionths. Okay, perfect. That is the correct answer. That's the same answer I've got. That's good. All right. I'm hoping that we're all nearly done. Can I ask, please, if you've got an answer, can you give me a thumbs up? Okay, well done. Okay. If your answer starts with a 4 and then has, well, 4,00 and then has 10 to the negative, then you're on the right track. Okay, it's a good sign. Okay, ladies and gentlemen, I don't want to take forever because I think there are some people who may not actually get to the right answer. It's not a criticism, it's just that I guess it's a fact at this point that some of you are still busy learning. As you learn, you can't always do everything immediately. All right, so here is what I did. I started off with the full formula because I want to make it really easy for the examiner to give me a mark. Only after I'd done the full formula did I go and replace that and that. Okay, so only afterwards did I go in and say, well, wait a second, E is equal to HF naught. Well, since this is W naught, I changed that to F naught. So only then did I go and plug everything in and split everything up. Just for the record, every single one of these splittings is on your periodic table. All right, sorry, not your periodic table, your formula sheet. Then what I did was I subbed in all of my values. It is quite a mission working with these big numbers, and it is very easy to make mistakes on your calculator. So it is so important that you show all of your substitution here because they'd give you marks there. In fact, if this here is out of 5 marks, you would get a mark for the formula, 1 mark for this side, 1 mark here, 1 mark here, and only 1 mark at the end for your answer. So as long as you've shown decent substitution of each of those, will you be certain that even if you do mess up, you can still get 80% of the marks without losing marks? If you don't show your substitution, then when it's wrong, you don't get any chance marks as well. All right. Can I quickly ask who got that one? Wait, there's a question. How do you get the mass for the kinetic energy formula? The mass for the kinetic energy formula is on your formula sheet. It's under ME. So if you go and have a look at your formula sheet, it's right at the top of all of your formula sheets. You'll see that you get the constants, and ME, the mass of an electron, is there. So is C, so is H. Okay, so a whole bunch of different constants are given there, and the mass of an electron is given there. It's very important that you know that the mass of an electron is given there, because nowhere in the question do they go, hint, look for the mass of an electron. And if you don't know what the mass of an electron is, you sit there with your jaw on the floor going, I don't know what to do next because I don't know what mass to put in. Or you make up a mass, which is probably just as bad. All right, so these values are given. You've got to, as you practice, get used to what's given on your formula sheet so that you use it and you don't waste extra brain capacity space trying to memorize things when you don't have to memorize them. All right, so I find that I'm very familiar with what's on my formula sheet because it effectively tells me what I have to work on memorizing, mainly my definitions, and what I can look up like my constants. All right, okay, so it then continues, and I am going to, I think we can clear from here. So I'm going to clear everything. So please just quickly take a screenshot. It'll just give me a little bit more space to work. So going back to here, it told us that in the original, the velocity or the maximum speed was 5.33 times 10 to the 5. It then says the photocell is now replaced with another photocell with a rubidium cathode. So we're using rubidium instead of potassium. The maximum speed of the ejected photoelectron is 6.1 times 10 to the 5 meters per second. That means that this is faster. Oh gosh, that is not how you write faster. This is faster. If it is faster, that means that my kinetic energy is larger. I can assume all of that from the comparison of those two values. Then it asks us, how does the work function of rubidium compare to that of potassium? Write down only greater than, smaller than, or equal to, and then explain your answer. I'm going to quickly pause here, and I'm going to give you a chance to figure out what you think the answer is. I'll check in just a second. Okay, good. That is the correct answer. Well done. Can I quickly ask who's already got an answer? Give me a thumbs up if you've got an answer. Good. Good. Okay, so the two people who sent me through check-ins, you're both 100% correct. Well done. Okay. Now, ladies and gentlemen, my answer here is that it is smaller than. I'd like to share a bit of a scary fact with you. You know that if you didn't answer 10.3, I don't even have to look at 10.4. You cannot get a mark. I know that sounds a bit ridiculous, but it's how we've started marking quite regularly in chemistry, and I'm assuming it goes to physics as well. But this answer is dependent on this. If this answer here is wrong, then we have what's called negative marking. Negative marking means that I can't mark correct logic to go with the wrong answer. If the answer is wrong, I don't have to look at your logic. Even if you'd written exactly what I've got here, if your answer above is greater than or equal to, you lose all 4 marks, even if you've written exactly what I've written here. So you need to make sure that your answer is correct. One of the things that's been a little bit scary that happened in the marking of last year's exams is if you left it blank. Some people have been told if you can't commit, leave it blank, and then they'll still give you the marks for the next bit. Last year in marking chemistry, if you left it blank, we didn't give you any marks. We treated a blank answer as a wrong answer, and then there was no positive marking. So please just be aware of that. It was one of the things that scared me quite a lot because it made me go, wait a second. We've always told our students, oh, it's okay if you leave it blank, rather you'll still get the marks. No, you won't, not anymore. It's not guaranteed. So please be careful. So I would answer this by putting out the formula. E is equal to W naught plus EK max. I then go and say, since the energy of the UV light or the photons doesn't change or stays the same, you may use any words, but the kinetic energy increases, the work, what's it called? The work function, okay, the words were coming out right. The work function must decrease. All right, technically the marks here would be for the energy remaining, the energy of the photon staying the same and the kinetic energy decreasing, and probably that relationship. I would say I couldn't really cut too much off here without potentially risking losing some of the 3 marks. So since it is 3 marks, 3 marks is rather generous. I would say here for 3 marks, I would insist on then putting in the formula, the energy of the photon staying the same and the kinetic energy, kinetic energy increasing. All right, ladies and gentlemen, we've still got about 7 more minutes. So I think I'm going to move on to the last question. We should manage to get through most of it, I'm hoping, in time. Okay. Maybe not. It looks like it's a long one, but maybe we'll get through some of it and you can do the rest as extra practice for later. Okay, so the question says, a learner uses a photocell to determine the maximum kinetic energy of the ejected photoelectrons. There are the values of the maximum kinetic energy. One photocell has a cesium cathode, there's our cesium, and the other has a sodium cathode, there's our sodium. Each photocell is irradiated, that means the same thing as having light incident on it or photons incident on it, by UV, ultraviolet light, from the same source. Same source means same frequency, same intensity, same everything. All right. The incomplete results obtained are shown in the table below. First question says, define the term work function of a metal. Because we've already done this today, I'm going to assume that you'd be able to do it again, and I'm just going to tell you the answer. It is the minimum amount of energy required in order to emit an electron from a metal. 10.2 says use the information in the table to calculate the wavelength of the ultraviolet light used in the experiment. This is relatively similar to what we've done before, so I'm hoping that you'll be able to do it relatively quickly. Okay, quickly go for it. You should have all the formulas written down already. All right, if you've got an answer, please type it in now. Okay, I didn't get the same answer, Michaela. I think I was close, but we're going to have to just quickly check. You're going to make me go back and check now. All right. Can I still get the same answer? It's kind of close to the one that I got previously. So my answer is also in the range of times 10 to the negative 7, which we got last time. Brilliant. Okay, Sarah, you're right. Okay. Michaela, just go and quickly have a look. Your powers are correct, but something's wrong with the value itself. Okay, brilliant. Yes, that answer is correct. I think it's Kaji. Oh, you're going to have to tell me there. Khadija. I hope I pronounced that correctly. You're going to have to tell me later at the end so that I get it correct. Okay. All right. Ladies and gentlemen, we're nearly out of time, so I'm going to quickly share the answer that I've got with you. Okay. So over here, what I did was I probably was a little bit silly. I probably shouldn't have done a mixture of substitution changes and plugging in, but I was halfway there before I realized I had. So you've got Planck's constant, you've got the speed of light, you've got the work function and the kinetic energy for cesium. You've got to use the information for cesium. It's the only way to do it. So here you'd work all the way down and get an answer of 3.5 times 10 to the negative 7 meters. Remove that. That's not a 1 and a 7. That's just times 10 to the negative 7 meters. All right. We're going to be out of time now, so I just quickly want to discuss how you do the rest of this question so that you can go and have a good look at it. It then asks you to calculate the maximum kinetic energy of an electron ejected from the sodium metal. Please note, in this case, you can actually use this information to know that that value is the energy of your photon. So all of them are going to have the same photon striking them, and the energy of the photon is 5.68 times 10 to the minus 19 joules, because it's going to be equal to this, and this is equal to all of this, which is equal to that value. Okay, that means you can know that that's the energy of your photon. You know the work function. You're looking for the kinetic energy. So to calculate the maximum kinetic energy, in fact, you know what? I'm just going to quickly do it because I'm halfway there already. I'm going to quickly do it. We're going to go a little bit over now. Not very much, just that we can quickly finish this calculation. Okay, so over here, the energy of the photon is 5.68 times 10 to the negative 19. The work function is 3,65 times 10 to the negative 19. And there is our kinetic energy. So 5.68 minus 3.65, we know they're both times 10 to the negative 19, gives me the kinetic energy is 2,03 times 10 to the negative 19 joules. Okay. Some people may have taken a little bit longer because they'd have gone all the way to do E is equal to HC over lambda to plug this value back in to eventually figure out that they'd actually already worked out the energy, but they're not necessarily going to give you additional marks. All right. Ladies and gentlemen, I think I'm going to call it a day there. Please take a screenshot of the last question just in case you want to continue with it, but I may organize for it to be one of the questions or a similar question will probably be covered in the masterclass. All right. Okay, I hope that that made good sense. It's always nice when we have an opportunity to practice some of the questions, and hopefully you have a better understanding of how the photoelectric effect works now.